Hello everyone. In this lesson, we're going to learn about how to perform data exploration and cleaning in Python. Now, the first part of really any data analysis or predictive modeling task is an initial exploration and cleaning of the data. When you first load a data set into Python, you don't really have a good sense of the different variables that it contains, the range of values those variables might take on, and whether there might be some errors or other oddities in the data that you have to take care of before you can carry out your analysis or modeling task. So this is going to be a fairly lengthy lesson where we are going to load in a real data set and go through the sorts of exploration and cleaning tasks that you might have to perform when you first are loading in and looking at a data set. So for this lesson, we're going to use the Titanic disaster training set on Kaggle as our motivating example. So we're going to just start by loading in some required packages and then the data set. So this code cell is just loading in some of the packages we're going to be using, and then we will read in our data. And now, after first loading in a data set, when you don't really have any idea of what it looks like yet, it's good to start by just getting some basic information by using some of the functions we've learned about in previous lessons. For instance, we could come down here and run .shape or check the .shape attribute just to see how big the data is. That's a good first step to run, because if the data is really large, we might have to think harder about how we're going to work with it, because some functions might be slow on a large data set. This data set, it turns out, is relatively small, so we shouldn't have to worry about anything running on it being particularly slow. Now let's also run .info. This will give us an idea of the different variables it contains and what types they are. So let's scroll down and look at the .info output. We can see we have several data columns. There's 12 in total, and we have 891 total records. Let's go ahead and look at some actual data entries or records by running .head. So here we're going to run Titanic train.head, look at the first 5 entries. And by inspecting some actual records, we can get a better idea of what sorts of data we're working with and what it looks like. So it looks like we have some passenger ID, survived passenger class columns, the name of the passenger, the fare that they paid, their ticket, and a cabin variable. I'm noticing right away, actually, that the cabin variable contains some not a number entries, so those are missing. So already we see that this data set is going to contain some missing values we're probably going to have to figure out how to deal with. So after gaining some sense of the types of records we have, let's run another summary function, describe, to get an idea of the distribution of these numerical columns. So we'll scroll down here and run Titanic train.describe. So this is pulling up summary statistics on each of the numeric columns. So we can see here, for instance, passenger ID. Well, this just seems to be a number going from 1 to 891. So essentially each row is just given a unique passenger ID, so that's not particularly interesting for us. The column survived is actually the target for prediction for this competition. So this variable actually tells us whether a given passenger survived the Titanic disaster or not. So that is actually one that's very important for us to look at. So let's see what that is. We can see the average of survived is 0.38. That means that approximately 38% of these passengers survived, which means most of them actually did not survive. Now notice that when we ran describe, it only kept the numeric columns because it can't run summary statistics on categorical columns. So we'll look at those separately here. Let's just make a list of the columns that are categorical. So to do that, we're going to make a list of the categorical columns with this construction here. Basically, all this is doing is saying we want to find the columns where the D type is an object, so that's things other than numbers. And we want to take the index of those columns, and we'll save those as the categorical columns. And then we're just going to use those column names to index back into Titanic Train to get only the categorical columns. And then we'll rerun .describe, but now since we're only running it on categorical columns, it will run a different describe operation that works on categories instead of the one that works on numeric columns. So let's run this and just see what the result is. we can see these are the categorical columns: name, sex, ticket, cabin, embarked. And when we run describe on this, it just gives us a table showing the count of each column, the number of unique different entries for each column, the top most frequently seen entry, and the frequency of the most seen entry. So for instance, under the sex column, it's showing us that there are 2 unique values here, so that's probably male and female. And then it's showing us top, the most common one is male, and there were 577 male entries. So as I alluded to earlier, when you load in a data set, it's sometimes hard to make sense of the different columns without some sort of external explanation as to what the columns mean, especially if the column titles are not very explanatory of what's in the column. So with this competition and with many other Kaggle competitions and other data sets you might find out there in the wild, you'll often have an accompanying document that provides some explanations as to what the columns actually mean. So this competition actually has that, and I've included in here the different variable descriptions. So in this box, it's just showing some explanations about what these variables mean. For instance, with the survived variable, a 0 means no, the person didn't survive, and a 1 means yes, they did. So the importance of any kind of documentation like this for what the different variables in a data set mean cannot be understated, because having a good understanding of the variables you're working with will be a great help in any sort of data analysis or prediction task that you're doing. So after loading in data and doing some basic exploration for the first time, there are several questions you should be asking yourself to get the data ready for analysis. So we're going to list what some of those are and then go through each one in turn and look at different methods for achieving it. So one thing that you want to always be thinking about after loading in a new data set is, do you actually need all of the variables? Oftentimes you'll have columns that either are just junk data that you don't want to use because they don't tell you anything, or they're data that aren't useful for whatever task you're trying to do, and by getting rid of it, you might be able to free up some memory space and also perhaps reduce unnecessary computation. So let's consider, with the Titanic disaster training data set that we loaded in, are there any variables we should think about getting rid of? Well, the point of this particular data set is predicting whether passengers on the Titanic disaster survived or not. So in terms of that end goal, we can kind of already see there's probably one variable that we could remove, the passenger ID variable, because when we were looking at the description of that variable, it was simply just a counter that was counting each of the rows, 1 through 891. So the passenger ID is just an arbitrary number that's been assigned to these different records and really has nothing to do with whether that person was going to survive or not. So for this task, we could safely remove that variable and probably would actually want to remove it. So let's start off by saying delete Titanic train passenger ID. Now, the numeric columns that we looked at, as well as the categorical ones that describe passengers in broad categories such as sex and class and age, those are things that would probably be somewhat useful for prediction. So I would say we should keep those. But we have a few other categorical variables that might be somewhat questionable as to whether they're going to be useful for prediction or not. Those would be the name variable, ticket, and cabin, because when we looked at those, they had a lot of different unique values, and it was unclear whether that would be something that would be useful for doing prediction. So let's start by looking at the name variable a little closer. We're going to sort it and then just look at the first 15 sorted names. So let's scroll down here and we see it's just a bunch of full names for passengers. And what really does a person's name tell you about whether they're going to survive or not? In fact, if we run describe on the name variable, we see that there are 891 unique names. That's not really a surprise. Every person has their own unique name. So unless we wanted to try to run some sort of text processing steps on these actual names, this is a variable we could probably remove for this prediction task, but in this case, it'd be nice to have some unique identifier for each of the records, and we already removed the passenger ID unique identifier, so for now we'll just keep this, but it's not something we probably want to use to be predicting with. Next, let's go ahead and look at the ticket variable. So we'll look at the first 15 entries of that. And we can see here the tickets really don't seem to have any rhyme or reason for their structure. We have ones that are just pure numbers. We have ones that are a mixture of letters and numbers, even like a slash in that one. Let's also run .describe on it to see how many different unique entries and whatnot we have. And we can see there are actually 681 unique cabins listed. So when a categorical variable has almost as many unique values as there are total records, it's usually suspect as in terms of whether it will be useful for prediction or not. We could try to reduce the number of different levels by somehow combining things into different groups, but I think in this case it's messy enough and there's enough unique values in it that I don't think we're going to use it. So let's go ahead and delete the ticket column as well. Now finally, let's look at that cabin column. We're going to pull up the first 15 rows for that. And when we look at that, we see there are quite a few missing or not a number values. And if we run describe on it, we see that there are fewer unique values this time. There are only 147 unique values, but there are also only 204 counted values because most of them are missing. Since most of the non-missing cabin values are unique, we could probably think that this isn't going to be useful for prediction, but we can also notice above that the cabins have a letter designation on them that is common across a lot of different numerical cabin numbers. So here we see C85, C123, C103. So in this case, this letter designation C could be a way of grouping categories together in a way that might actually be logical. Say there might be a section C on the ship where all of these different C-numbered cabins are in that area, and it could be that a certain designated section like that in the ship, people were more likely to die in that area or survive depending on how the crash happened and where the section was located. So this variable still might actually have some value for us in prediction if we can extract that information into some meaningful groups. So we will leave the cabin variable here for now and see if we can deal with that later. So now that we've considered whether we should remove variables, we should also be considering, should you transform any variables? For instance, when you first load a data set, some of your variables might be encoded as data types that don't fit particularly well with what you're trying to do. For instance, if your data had, say, dates, and they were loaded in as strings or numbers and you wanted them as dates, well, you might have to convert them to actual date objects. In our data set, the survived variable was loaded in as zeros or ones depending on whether they survived or died. But if that's not such a nice way of thinking about it, it'd probably be easier to think about if we just had the full string died or survived, so we don't have to think about it in terms of zeros and ones. So as a simple example of a transformation, we could turn the survived column into categorical. To cast something as a categorical variable, we can use the pandas function pd.categorical. And then we will pass in the column survive that we want to transform. So after we do that and save it as a new variable, we'll also run this operation on it to change the names of the categories. So we're going to take our new survived data and rename the categories to these, died and survived. After we do that, we can run .describe on our new variable just to look at a table of it now. So now we have some nice categories that are easy to understand. And we can see the frequencies here, where 61% of people died and 38-ish% survived. We also noticed another variable earlier that actually has questionable data encoding, and that is the p-class or class variable. The p-class has 3 different values, 1 for being first class, 2 for being second class, and 3 for being third class. This variable was loaded in as an integer number, even though we know intuitively that passenger classes are actually categories. So it doesn't make a lot of sense to encode that as a numeric or integer variable. What's more, first class would be considered to be above or higher than second class, but first class was encoded as the integer 1, which is actually before or lower than 2. So we could address this by transforming the p-class variable into an ordered categorical variable. So we'll show how to do that here. Again, we can run pd.categorical on our p-class column. And to make it an ordered categorical variable, we can add this additional argument. So comma ordered equals true. And after creating this new p-class variable that's categorical, we'll just do .rename categories again so we can give them names that we can easily understand. Class 1, Class 2, Class 3. And now instead of a numerical summary that perhaps wasn't particularly useful before, we get a summary of the categorical version of p-class. And this gives us a bit more interesting information here. We can see that about 25% of the passengers here were in first class, 20% were in second class, and 55% were in third class. So let's go ahead and overwrite our original p-class variable with this new categorical version. And now it's time to revisit our cabin variable that we didn't remove before. If we run .unique on cabin, we can see that it has a bunch of unique values, but again, many of them start with the same letter designation. We have like C, E, B, A. So let's group the cabins by the letter designation, and hopefully we can reduce the number of unique categories and perhaps extract something useful from this variable. So what we want to do here is just extract the first letter of each of these cabin strings and then create a new categorical variable that's just based on that letter instead of the numerical portion. So we'll show how we could do that below. We're going to start by getting the cabin variable. That's what this is doing. Then we're going to first encode it as type string because when we loaded everything in, they were encoded as object types. Now we're going to run a list comprehension on this column to extract the first letter from each record. So this is the list comprehension we're going to run here. Cabin 0, that's saying get the first letter for each cabin in the cabin variable that we just saved. So this list comprehension is stripping off the first letter of every single record of the variable. And then we're just wrapping this whole thing in np.array to turn this into a numpy array. We're running pd.categorical on the array to transform it into a new categorical variable. And now we'll run describe on that new variable to check what we got here. So we can see after running this, we have managed to condense that cabin variable down into much fewer categories. So although many of the variables were missing here, these are the missing ones, 77% didn't have a cabin listed, we have far fewer unique categories, so some of these might actually be useful for prediction. For instance, there were almost 60 people in the C area of the ship, 47 people in the B area, and quite a number in the D and E areas. So potentially that could be useful for prediction. For instance, if area D was the spot on the ship where the crash occurred, perhaps everyone in that whole section didn't survive. And if that was the case, this D variable could be a powerful predictor for not surviving. Since this could potentially be useful, let's go ahead and save over the original cabin variable with our new cabin variable. Now that we've done some variable transformations, another question that we should consider is, are there any NA or missing values, outliers, or other strange values we should deal with before proceeding with any kind of analysis? In Python, using the pandas library, you can detect whether there are any missing values with pd.isNull. So we'll just give an example of doing that. We'll create a dummy vector of data that contains some none or missing values, and then we'll run .isNull on this dummy vector, and it'll just produce logical output where if the value is missing or null, a true will be listed, and if it is not, a false will be listed. So we can see in this case, index position 1 and 3 were true because we put missing or none values in for those. So identifying missing values is the easy part. It's much harder to decide exactly how to handle them. For instance, if we check the age variable in the Titanic data and run .describe on it, we see that the count here is actually fewer than the total number of records. So let's identify the indices where these missing age values occur. We can use the isNull construction that we made earlier to do this. So we can use the same construction above, Titanic train age is null, and we want to check where that is true, and we're going to use this whole thing within an np.where clause. It will extract the corresponding indices. So by running this, we're going to get all of the indices where the value is missing. So here we have an array of indices where the corresponding age value is missing. And this is quite a few missing values, so we definitely need to do something with this before we continue with our prediction task. So when you see missing values in a data set, there are a number of different things you could consider doing to them. One, you could replace all the null values with zeros, if you happen to be working with numeric data anyway. You could replace all of the missing values with some central value, like the mean or median of the column. You could try to impute some other value. Imputation means using some sort of algorithm to fill in the values. In fact, mean and median are simple forms of imputation, but there are other more complicated forms of imputation, say using data in other columns to try to make a guess at what would be reasonable values for the age column. Another possibility would be splitting the dataset into two parts, one where the age variable is not missing, and the other where it is missing. Now, setting all of the missing ages to some central number, like the median or mean age, could be a reasonable thing to do, except we don't know exactly what the distribution of the age variable looks like yet. So to do that, we could pull up a quick histogram of the age variable to see if it looks like a fairly normally distributed variable, and if it is, perhaps using the mean or median would be a reasonable thing to do. So we'll show how to make a simple histogram in pandas. You pass the name of the data frame, .hist, and then within this you say column equals whatever column you want to plot. And these are just specifying the size of the figure and the number of bins we want in the histogram. When we run this, we should create a histogram of the age column. So we can see that while there is some concentration of ages at the low end, so there were some younger people on the ship, in general, the data seems to follow a somewhat normal pattern here. So perhaps setting the missing values to some middle value age between, say, 25 or 30 might be a reasonable thing to do. So let's go ahead and set the missing age values to the median value of 28. And we'll show how to do that below. So we can use the np.where function to do this. We will say np.where, then a logical check. In this case, we want to check where Titanic train age is null. And when this is true, we're going to set the value to 28. And where this is false, we're just going to keep the original value that's actually there. And that will give us our new age variable. And we'll just overwrite the original age variable with our new one. And then we'll run .describe on it to just confirm that we do indeed have a count of 891 now. So all of those missing values were overwritten. Let's go ahead and rerun our histogram as well, just to get a sense of what the data look like now. You can see that by assigning all the missing values a value of 28, this bin where 28 lies is much taller now because there's a whole bunch of extra values in there. Now clearly some of these age values we imputed with the median are going to be quite a bit off from their actual values. On the other hand, doing this might be better than throwing entire records away. These are the sorts of decisions you'll have to be making in data analysis projects oftentimes, and there's often really no one right answer as to what the best thing to do is. It often is just a matter of having experience and knowing a lot about the domain that you're working in. Now let's consider outliers. Outliers are extreme values that lie far away from the typical values within a distribution. If a data set has some extreme outliers, they can have significant negative impacts on various predictive modeling techniques, so it's good to identify them and perhaps do something to them to deal with that. To look at some outliers, let's check the fair variable. I'm going to run .plot kind box on it to make a box plot, and this sort of plot is good for detecting outliers. Here we see on the box plot, this green line is the median value, and this blue box contains the middle 50% of values. So some of these circles above the box are way above the median. So out of interest, let's determine who actually was this person or people that paid so much for their tickets. So to do that, we can run np.where on the fair column, where the fair is equal to the max of that column, because we want to see who the biggest one was, so that should be the max. And if we do that, save that index, and use it to index into the data set, we can find who that person is. So we can see there's actually 3 people that all paid the same amount. They paid 512, either dollars or pounds or whatever the fair value is. And all of these people were in first class. Well, you should hope that they would be if they paid so much. Now, similar to NA or missing values, there's no single cure for what to do with outliers. We could keep them in, we could delete them, we could try to transform them in some way to reduce their impact, or select modeling techniques that are not badly affected by outliers. But it's still worth identifying them and keeping them in the back of your mind because they can have a disproportionately large influence on your results. So we're going to keep these high rollers in our data set, but it's a good thing we know that they're there. One final thing to consider is, should we create any new variables? So when you first load in a data set, the variables that you are given aren't always the most useful ones for prediction. Creating some new variables that are derivations or combinations of the existing ones that you're given is a common step that can help you create some more useful information for whatever task you're working on. This process of creating new variables is known as feature engineering. Now, creating a new variable can be as simple as just adding, subtracting, multiplying, or dividing two numeric variables together. So we'll give an example of how we could do that. So in the data set, we had some variables related to family, one that told how many siblings a person had on board, and another that told how many parents the person had on board. Well, if we added those two things together, it would just be an overall metric that showed how many family members they had on board. So we could easily create a new variable called family that's just the sum of those two things. So we'll run that to create a family variable. And now that we have that, for interest's sake, let's see who had the most family on board. So to do that, we can take our new variable, family, check where it is equal to the max of itself, and run np.where on that whole thing to find the indices where that is true. Then we can take these indices to index back into the data set to extract those records. So when we run that, we can see that there are several people actually that had 10 family members on board and that had 8 siblings on board. So all of these different people were actually siblings of each other. And sadly, all 7 of these siblings have 0 listed under the survived column. So that means none of these siblings survived the Titanic disaster. So to wrap up, in this lesson, we covered several general questions that you should think about addressing when you first inspect a data set. Your first goal when you load in some data is to explore its structure and then prepare the variables for your analysis. Only after you have cleaned the data and gotten it into a format that you can work with can you move on and do more complicated analyses and prediction tasks. Since data cleaning and formatting is a very important and often time-consuming part of data analysis, it's important that we spend some time learning how to work with different types of data and how to manipulate data better. So over the next few lessons, we'll go more in depth as to how to clean and pre-process different sorts of data, including text data, numeric data, and dates. If you found this video useful, you can drop a like, hit subscribe, and I will see you again next time.